This lesson is about vector valued functions. Let's see what these functions are. Suppose t is a real variable, so let t be a real variable. So we define a function of t, but the values of the function are vectors. So a function r of t whose value at any t is a vector like this. For example, I can use ft, gt, ht, and for a specific function, f, g, and h are given. This defines a vector function, is a vector valued function. If I want to use the other notation that we have used for the vectors, instead of this notation, I can definitely use, like I can rewrite this as ft times I plus gt times j plus ht times k. By times, I mean a scalar multiplication. So f of t is scalar multiplication vector I, gt scalar multiplication vector j, and ht scalar multiplication vector k. It's also the way that I define this is in the three-dimensional space. So this gives me a function whose values are in the three-dimensional space because we have three dimensions, three coordinates. But of course, it could be two-dimensional. I mean that we might have two coordinates. We can also define the vector valued function with two coordinates. What do I mean by two coordinates? It means that like r of t is the vector consisting of two coordinates, ft and gt. Or in terms of the other notation, I can show that by ft I plus gt j. Okay, now let's see. Let me go back to that situation that RT has three coordinates. What is typically represented by this? So this R of t, which has three coordinates, this represents a curve in the three-dimensional space. Like suppose this is x, y, z coordinate system, x, y, z. And I assume that f, g, and h are continuous functions. in the sense that we know from calculus 1. And suppose t runs from a number a to some number b. So at a, we have the vector of RA, which is FAGAHA. Suppose that's the vector RA. And the end point is the point FAGAHA. As t changes and it gets bigger and bigger, goes to b, we will see a curve in the three-dimensional space. Depending on f, g, and h, this curve might have different shapes. So at the end, we get to this vector RB. So for every t, suppose I pick one, say t1 in this interval, R of t1 will be a vector initiating from the origin and ending or terminating at a point on that curve. So this is R of like t1. So in fact, those end points or those terminal points of the curve of the vectors, they form that curve. So again, let me repeat. The terminal points of all of those curves, they form this curve that you see here. These are the terminal points of the vectors, initiating from the origin, ending at a point on that curve. So this curve shows the terminal points of those vectors. Of course, if instead of three-dimensional case, if I have two-dimensional case, suppose I have RT equals FT and GT, and T runs from A to B. We don't need a z-axis, just X and Y. Suppose at A, we have this vector. This is RA. And at B, when T is B, we get this vector RB. Depending on those F and G, we might have a curve connecting these two. At any point T1 from A to B, a vector of RT1 will be a vector initiating from the origin and terminating at the point on the curve. So in fact, all those terminal points together, they form this curve. In these two pictures, I chose examples that t was running from a number to another number. Both of numbers were finite. In the case of minus or plus infinity, we don't definitely have that equal to infinity or minus infinity. So instead of this t, we have t is more than minus infinity, less than infinity. Although minus infinity and infinity are not numbers, but we know that roughly speaking, any number is more than minus infinity and less than infinity. So in this situation, we don't have a starting point of the curve and ending point of the curve. The same situation in the higher dimension, t is strictly more than minus infinity or so when this happens, it's possible that we have like in this picture that we have a curve and It doesn't have any specific starting point and ending point because t is running from minus infinity to plus infinity, and the function r of t is the vector ft gt ht. So at any number, at any real number t1, the vector rt1 will be a vector connecting the origin of the coordinate system to a point on the curve. As a simple example that we are familiar with, we can have an equation or a vector valued function that represents a line in the space. This is similar to the examples that we have seen before. So find RT. Of course, in those examples before, I said that find the equation of the line connecting two points. And I said find the vector equation and also the parametric equation of the line connecting 2 points. But here, instead of saying vector equation of the line, that's a vector valued function RT. Find RT, which is to represent the equation of a line passing through we have 2 points, P consisting of 0, 1, 3, and Q is 2, 5, 4. Again, let me write the equation of the line, but that equation, we write it as one vector with 3 coordinates, and that will be a vector valued function. As you might remember, since we want to connect P to Q, I can look at the vector V, which connects P to Q. First coordinate of Q minus first coordinate of P2 minus 0 is 2. Second coordinate of Q minus second coordinate of P, 5 minus 1 is 4. Third coordinate of Q minus third coordinate of P, 4 minus 3 is 1. So this is the direction vector that shows the vector from P to Q. And if you might remember, the equation of the line was the first, I can look at the first point as a vector, 0, 1, 3, plus t times the vector connecting these two. Excuse me, so sorry. The vector connecting these two is this vector, 2, 4, 1. But here, to find R of t, in fact, this is R of t, we go a little bit further than that because we want to write this R of t with 3 coordinates in terms of t. So this t is multiplied by all of these 3 coordinates. So this is 0 plus 2t, just 2t. 1 plus 4t, or 4t plus 1, or 1 plus 40, same thing. And 3 plus t times 1, or t plus 3. In fact, this is the vector valued function, which represents the equation of the line, or in fact, it represents the line which connects these 2 points. If you might remember, when we talked about a vector equation of a line, like this example in the before, we stopped here for the equation, for the vector equation of the line. But as a vector valued function RT, we go one further step and write it this way, the way that we did at the last line. One important thing that you should consider, since it's a line, it has no restriction for the value of t. T can be any real number. So I should specify here, this is for all the t's, strictly more than minus infinity, less than infinity. So for different values of t, we get different vectors, and the terminal point of all of those vectors, they will form the line connecting P to Q. So I chose this example because this was very close to what we have done before in terms of the vector equation of a line. I need to point out that if in this problem we were required to write our answer in terms of ijk, the final answer would be, let me write that also. So this is the answer when you use this notation for the vectors. If we are required to write our answer in terms of ijk, obviously this is going to be r of t equals 2t I plus 4t plus 1 j plus t plus 3 k, and still for the same values of t, for t more than minus infinity and less than infinity. So these two answers are the same, just in different notations of the vectors. One of the things that we should pay attention to when we deal with vector valued functions is the domain of the function. Let me give an example to see that how we find the domain of a vector valued function. Let r of t, or a vector valued function, be defined this way. Suppose it is sine of t times I plus radical t times j plus e to the power of t times k. By times, again, I mean a scalar multiplication. So I, j, k are those standard unit vectors that we are familiar with, and coefficients are sine t, radical t, and e to the power of t. So as t changes, we get different values, and this will give us a curve in the three-dimensional space. Here, in this example, our concern is not the graph of that. The concern is the domain, meaning that which values of t, the set of all values of t that for which this expression makes sense. So suppose I denote it by d. Obviously, sine of t is defined for every real valued function, for every real valued variable. So t could be anything. So I have no restriction here. The same with e to the power of t. E to the power of t for any real value is defined. The only thing which has problem here is radical t, which should be t must be more than or equal to 0. So therefore, the domain is all the t such that, as you know, that we draw this vertical line to show for such that, or we use colon, either one are standard, such that t is more than or equal to 0. Okay, but sometimes we have restrictions for every components of the vector valued function, like the next example, that r of t is say radical t times I plus 3 over t times j plus a radical of t squared minus 1 times k. And I want to find the domain. So each of these three components, they have their own restrictions. Radical t requires that t be more than or equal to 0. 3 over t requires that t be different from 0. Radical t squared minus 1. It requires t squared minus 1 should be more than 0. But t squared minus 1 is more than or equal to 0. We have you have seen in more elementary courses this kind of inequalities to solve. So you should be familiar with solving these kind of inequalities. As you might remember, this consists of t squared minus 1 is more than or equal to 0, consists of two intervals. One is t is more than or equal to 1, or t is less than or equal to -1. Now, I should find the overlapping of these three restrictions. So t must be more than or equal to 0. T cannot be 0. And also t must be either more than or equal to 1 or less than or equal to -1. If you think a little bit about this, I will suggest that before seeing my solution, think on all the examples that we do. We will see that the overlapping of all of these answers is t such that t is more than or equal to 1. This domain satisfies all of these three conditions at the same time. Let me also give an example that we have real valued functions with two coordinates that will be also possible to see these kind of examples, like r of t. So let's R of t consists of radical t I and I'm sorry, not this notation anymore because I'm using I and j. So plus radical of 4 minus t squared j. So it's a curve in the plane. We don't have k here, just I and j. And I want to find the domain. The domain D. So each of these two components has its own restrictions. I should find the overlapping of these two. Radical t, the restriction is t must be more than or equal to 0. Radical 4 minus t squared, its restriction is 4 minus t squared. Must be more than or equal to 0. Here 4 minus t squared, not t squared minus 4. 4 minus t squared is more than or equal to 0. As you know, again, these are the kind of things that you have seen in more elementary courses. T must be from minus 2 to plus 2. Now, the intersection of these two conditions, t must be more than or equal to 0, and t must be from minus 2 to plus 2. The intersection is all the t's such that t is more than or equal to 0, less than or equal to 2.